For a long, long time, software developers lived by an unwritten rule. Basically, ignore the machine. But that's all changing. Today, we're diving into something called mechanical sympathy and figuring out why getting to know the hardware, the actual silicon, is suddenly the most important thing for performance. For the longest time, software and hardware, they had this really simple, kind of comfortable deal. It was like this golden contract that basically built the entire tech industry as we know it. And that rule was simple. Don't worry about the hardware. It's just going to get faster. I mean, you could write messy, inefficient code and it just didn't matter because you just knew that the next generation of chips would come along and like magic, make your slow software fly. And yeah, they had a name for it, the free lunch. I mean, think about it. Every 18 months or so, Moore's Law silves up a brand new, faster CPU. And just like that, developers got a massive performance boost for doing absolutely nothing. What a deal, right? But then, around the mid-2000s, the free launch was over. Just gone. It was abrupt. Those predictable, amazing performance gains we all took for granted, they just stopped. So what on earth happened? Why did the music suddenly stop? This quote from Henry Petrosky just hits the nail on the head. It perfectly captures the tension that was building up. For years, you had all this inefficient software, but it was completely hidden by these staggering gains in hardware. But the second that hardware progress slammed into a brick wall, well, all that software wastefulness was suddenly out there for everyone to see. And if you look at this timeline, you can just see it. This beautiful, almost perfect curve for decades where hardware just kept getting better and better. And then, bam, right around 2005, the line just goes flat. And it wasn't because engineers got lazy, nope. It was because they ran face first into the cold, hard laws of physics. First up was something called the power wall. See, as we crammed more and more transistors onto a chip, the heat they generated went through the roof. CPUs got so ridiculously hot that we literally couldn't cool them down fast enough. And just like that, the race for more gigahertz, it was over. Next, they hit the memory wall. The problem was that CPUs got incredibly fast, but the main memory, the RAM, just couldn't keep up. The gap between them became this huge canyon. Your CPU could do hundreds of things in the time it took to just get one piece of data from memory. So you had these super powerful processors just sitting there, twiddling their thumbs, starving for data. And the final nail in the coffin was the instruction-level parallelism wall. For a while, chip designers used all these clever tricks to make a single CPU core do more things at once. But eventually, it just got too complicated. The effort it took to find those tiny bits of extra parallelism just wasn't worth the reward anymore. All the low-hanging fruit was gone. Okay, so if hardware isn't getting faster on its own, what do we do? How do we get more speed? Well, the answer, weirdly enough, comes from Formula One racing. The legendary driver, Sir Jackie Stewart, said it best. He said the greatest drivers have what he called mechanical sympathy. It's this deep, intuitive understanding of their car. They don't fight the machine, they work with it. And that right there, that's the new way of thinking for software. We have to stop treating the computer like some magic black box. Instead, we have to really understand how the CPU, how the cache, how memory actually works, and then write our software to play to those strengths, to be in harmony with the hardware. Okay, so that sounds great in theory, but what does it actually look like? Let's dive into what I'm calling the 3 alchemies of performance. These are real techniques where understanding the machine leads to performance gains that honestly feel like magic. All right, first up, the CPU cache. The best way to think about this is imagine your main memory, your RAM, is a giant library across the street. Every time you need a book, a piece of data, you gotta make that slow trip. Now the cache, that's like a magical bookshelf right next to your desk. When you go get one book, the CPU is smart enough to grab the entire shelf that book was on and put it on your personal bookshelf. The whole game is to make sure the next book you need is already sitting right there, waiting for you. So how does that apply to writing code? Well, the old school way tends to mix all kinds of data together. It's like putting a cookbook next to a novel, next to a phone book on your magic bookshelf. You're wasting precious space. The data-oriented way, though, groups all the same kind of data together. So when you ask for one character's position, the cache loads up the positions for the next 15 characters for free. Every single byte it fetches is something you're probably going to need. It's incredibly efficient. And look at this. This chart shows you just how big a deal this is. We're not talking about a 5 or 10% improvement. We're talking about a potential 70 times speed up, just by rearranging how your data is laid out in memory. It's the same computer, the same logic. The only thing that changed is that we started thinking about the hardware. That, right there, is mechanical sympathy. Okay, alchemy number 2, memory architecture. On a traditional PC, think of the CPU and GPU as having their own little workshops, each with their own memory. To share data, they have to slowly copy it back and forth down this long, slow hallway. It's a huge bottleneck. What Apple did with their unified memory is they just knocked down the walls. Now it's one giant universal workbench. The CPU and GPU can work on the exact same piece of data at the same time with zero slow copying. It's a game changer. And for our third alchemy, let's talk about AI hardware, like Google's TPU. A normal CPU is like one person running back and forth to a warehouse to get parts. It's a lot of wasted motion. A TPU, on the other hand, is like a massive bucket brigade, a long line of workers. The data just flows down the line from one worker to the next in this perfect rhythmic way. Every single worker is busy on every single clock cycle. It's an architecture designed from the ground up to completely avoid that memory bottleneck we talked about. So, here's the cool part. The end of the free lunch wasn't a tragedy. It was actually the beginning of something amazing. It kicked off this Cambrian explosion of new, specialized hardware. The era of the one-size-fits-all CPU being the king of the hell, yeah, that's over. What we have now is what's called a heterogeneous world. You've got your general-purpose CPUs that are great for quick, sequential tasks. You've got your GPUs, which are these massive parallel processing beasts, perfect for things like graphics or training AI. And then you have things like TPUs, which are hyper-specialized for doing just one thing, the specific math for machine learning, but doing it insanely fast. And this table really breaks it down. A CPU is all about low latency, getting one job done fast. A GPU is all about throughput, doing a million jobs at once. And a TPU is laser-focused on one specific kind of math. If you try to write code that's hardware-agnostic, that doesn't care which one it's running on, you are just leaving an unbelievable amount of performance on the table. It's that simple. And look, this isn't just some abstract theoretical idea. Thinking this way, being aware of the hardware, is becoming a massive competitive edge out in the real world. So who's actually putting this into practice and winning because of it? The answer is the best companies are. You see Cloudflare writing custom CUDA code that runs only on specific NVIDIA GPUs. You have Netflix digging into low-level CPU data to fix tiny cache problems that save them millions. And then you have whole industries like game development and high-frequency trading. They've been operating this way for more than a decade. They get it. Performance is a feature. And all of this is fundamentally changing what it means to be an elite engineer. Look, building abstractions is still a vital skill. But the thing that really separates the best from the rest now, it's knowing when an abstraction is hurting you more than it's helping you. It's having the skill, and frankly, the courage, to tear it down and get your hands dirty with the hardware itself. Which really brings us to the final big question. For decades, the goal was always to be hardware agnostic, to write code that could run anywhere. That was seen as the ideal. But now, in this new age of wildly specialized silicon, you have to wonder, is being hardware agnostic still a feature, or has it actually become a bug?